What's a Bose-Einstein condensate? Does it have anything to do with penguins?
We all know that ice is pretty cold. It forms at 0 degrees Celsius when water undergoes a phase change from liquid to solid. But is that the only phase change that happens as we reach ever colder temperatures? Is there something colder than solids? Let's start with carbon dioxide. At Earth's surface, CO2 is a gas, but as you cool it down, it too eventually freezes. At minus 78 degrees Celsius, carbon dioxide becomes a solid, commonly known as dry ice. Liquid nitrogen is even colder. We have to cool nitrogen gas down to minus 196 degrees Celsius for it to become a liquid. The darkest regions of outer space clock in at a toasty minus 270 degrees Celsius, only 3 degrees above absolute zero. The energy for this temperature comes from the leftover light from the Big Bang itself. The coldest naturally occurring place we know about is the Boomerang Nebula, about 5,000 light years away. The gas in the nebula has been expanding for so long that it has cooled to just 1 degree above absolute zero. 0 Kelvin, or minus 273.15 degrees Celsius, is the point at which no additional heat can be extracted from an object. For reasons we'll explore later, this temperature can never actually be achieved, but scientists have gotten impressively close. How close? About 1/billionth of a degree above absolute zero, a nanokelvin. Wow, that might be even too cold for us Canadians. To the best of our knowledge, the coldest temperatures ever achieved in the universe have been in labs right here on Earth. At such temperatures, a strange new state of matter arises that few of us are familiar with, a Bose-Einstein condensate. This state of matter was first theorized by Albert Einstein in the 1920s. He used theories of quantum statistics put forward by Indian physicist Satyendra Bose to predict what would happen to matter at such cold temperatures. The results suggested that at very low temperatures, often on the nano or picokelvin scale, matter would behave very differently, in a way similar to how penguins deal with cold winters. Look at these happy little penguins from southern Chile. The temperature is warm enough that you can identify the positions and velocities of individual penguins in a 3D space. Now, if we go to the South Pole, the coldest place on Earth, the temperature drops down to minus 60 degrees Celsius. The birds huddle together so close that it becomes difficult to tell one penguin apart from another. They essentially become a single unit, a winter penguin condensate, if you like. Bose-Einstein condensates, or BECs, are very similar. When the critical temperature determined by this equation is achieved, the atoms in the system stop behaving like strong independent units of mass, and instead they condense into a single unit, the properties of which aren't defined by the Maxwell-Boltzmann distribution we're familiar with. Maxwell-Boltzmann distributions are used to describe the behavior of particles or atoms when the temperature is high enough or the particle density is low enough that quantum effects are negligible. For a slightly more complete picture of how particles interact, we must consult Enrico Fermi and Paul Dirac and use their quantum statistics model dubbed, unsurprisingly, Fermi-Dirac statistics. It turns out that a class of particles known as bosons stop following Fermi-Dirac statistics at sufficiently low temperatures. Instead, they follow Bose-Einstein statistics. Maxwell-Boltzmann, Fermi-Dirac, Bose-Einstein. At least now we have the answer to the age-old joke, how many physicists does it take to screw in a particle statistics model?
I want to know the history of Bose-Einstein condensates. How did scientists manage to cool things down to temperatures? Also, what are some of the applications of this Bose-Einstein condensate?
Bose-Einstein condensates are named for the two scientists who first theorized their existence. You're likely already familiar with noted wacky picture enthusiast Albert Einstein. Einstein is famous for his many novel scientific ideas, one of which being the quantum of light, what we would call a photon. Bose is seen here in the exact opposite of a wacky picture. At the turn of the 20th century, Max Planck found that there was no physical model that could properly explain the spectrum of blackbody radiation, and in a desperate grasp at a solution, found that treating radiation as if it were made up of discrete units gave a far superior model of the blackbody spectrum. Many do not give much merit to Planck's assertion, but it did gain the attention of a young physicist by the name of Albert Einstein. Carrying on the concept of discreteness, Einstein considered that light itself might be quantized. He attempted to demonstrate this by the photoelectric effect, which would eventually win him the Nobel Prize in Physics in 1921. Einstein's explanation of the photoelectric effect has been called the birth of quantum physics, and there was an explosion of theories in the following years. Satyendra Bose of boson fame was born in Calcutta in 1894 and excelled at every institution he attended. In the 1920s, he extended on ideas of the relatively new quantum theory. In particular, Bose theorized that the Maxwell-Boltzmann distribution would not be sufficient to describe photons. A very brief interpretation of the part of quantum theory that applies here is that photons having the same energy are indistinguishable from each other. This hitch necessitated the development of a different way of statistically modeling groups of photons, and Bose used this model to derive Planck's radiation law. However, he had difficulties in getting his paper published. Bose had some familiarity with Einstein, having previously received his blessing to translate his paper on generalized relativity into English. Bose sent his theory to Einstein with the instructions that if his paper was acceptable, it was to be published. Einstein approved and submitted the paper to be published, which benefited from the name recognition. Einstein published 2 papers of his own extending on Bose's work, realizing that the same might be true not just for photons, but also atoms. The culmination of these papers was Bose-Einstein statistics. The temperatures required are reaching absolute zero, and the capability to produce these conditions did not exist at that time, or even in the lifetime of Bose and Einstein. With no practical method for testing, the Bose-Einstein condensate sat on the shelf untouched as some theoretical oddity for 70 years. Magnetic cooling was required to reach these very cold temperatures. Magnetic cooling was first put into use for cryogenics in 1933. Continued improvements in magnetic confinement brought the Bose-Einstein condensate into the realm of reality. As with most everything else, the introduction of lasers opened up new possibilities. The first instance of a Bose-Einstein condensate was created in 1995 and was maintained for 15 seconds. This was achieved by suspending rubidium in a magnetic field and using a combination of laser and evaporative cooling. Wieman, Cornell, and Ketterle received the Nobel Prize in 2001 for the production and study of Bose-Einstein condensates. 2014 saw Bose-Einstein condensate-like properties displayed under very specific conditions at room temperature. Clearly, Bose-Einstein condensates are a fascinating field of study. Let's take a closer look at the science behind how a Bose-Einstein condensate is produced.
So what exactly is going on here? The most important part of a Bose-Einstein condensate are the bosons. Bosons are any particles that do not follow the Pauli exclusion principle and have an integer spin value. The primary example of bosons are photons, but there are a lot of other examples as well. One of these that we will look at later is helium-4. Another characteristic of the bosons is that at low temperatures, they obey Bose-Einstein statistics. Bose-Einstein statistics are applied to bosons where certain conditions are achieved. At this point, the particles no longer follow a Maxwell-Boltzmann statistics model. As shown in the inequality beside me, where n is the number of particles, v is the volume, and n sub q is the quantum concentration. This is most easily achieved at extremely low temperatures. For bosons, this occurs within a billionth of absolute zero. When we get to these temperatures is where the condensate is formed. The condensate is a state of matter exclusive to bosons. Similar to how a plasma is formed at extremely high temperatures, a condensate is formed at extremely low temperatures. A characteristic of the condensate is that it behaves as a single superatom. This allows for some interesting applications, such as observing quantum effects at a macroscopic scale. This is possible because all of the particles in the grouping occur at the same state at the same location. One interesting characteristic of this state is in superfluidity. A superfluid has zero viscosity since the fluid acts as a single particle and cannot interfere with itself. Helium-4 is an excellent example of this. Next, you will see some footage of the helium-4 superfluid, and after watching, the implications will be clear.
This rapidly evaporating liquid helium cools until at 2 degrees above absolute zero, a dramatic transformation takes place.
Suddenly, you see that the bubbling stops and that the surface of the liquid helium is completely still. The temperature is actually being lowered even further now, but nothing particularly is happening. Well, this is really one of the great phenomena in 20th century physics.
The liquid helium had turned into a superfluid, which displays some really odd properties.
Here I have a beaker with an unglazed ceramic bottom of ultrafine porosity.
Ordinarily, this container with tiny pores can hold liquid helium. But the moment the helium turns superfluid, it leaks through. Superfluid helium can do things we might have believed impossible. It appears to defy gravity, a thin film can climb walls and escape its container. This is because a superfluid has zero viscosity.
Okay, that's a great party trick, but does it have any real applications besides making jars feel completely useless?
There are various applications in Bose-Einstein condensates like atom lasers and etching, which I'll be talking more about in the next couple of minutes. Other applications are sensitive measurements and instruments, improved ability to manipulate matter waves, laser gyroscopes, accelerators, and honestly, stuff we can't even imagine yet. Most research into Bose-Einstein condensates serves as basic research. That is to say, it is more concentrated with knowing more about the world in general than with implementing a specific technology. However, there are several potential test uses for Bose-Einstein condensates. The most promising one is in etching. Etching is the act or process of making designs or pictures in a metal plate, glass, etc. When Bose-Einstein condensates are fashioned into a beam, they are like a laser. That is to say, both a laser and a Bose-Einstein condensate beam run in lockstep, guaranteeing that an experimenter will know how any part of the beam will behave. This property of lasers has been used in the past for etching purposes. A Bose-Einstein condensate beam would have greater precision and energy than a laser because even at their low kinetic energy state, the massive particles would be more energetic than the massless photons. The major technological concerns of the Bose-Einstein condensate beam would be getting a clean enough environment for it to function repeatedly, and reducing the cost of Bose-Einstein condensate creation enough to use it regularly in beams. However, Bose-Einstein condensate beams or atom lasers could produce precisely trimmed objects down to a very small scale, possibly a nanotech scale. A summary of Bose-Einstein condensate is that it was predicted early by Bose and Einstein and was achieved tens of years later, which inspired a lot of related technologies. Bose-Einstein condensates in lab experiments are very fragile since they need extremely low temperature and density levels. It can also be used in ultra-sensitive measurements, for example lasers or Bose-Einstein condensate beams. Bose-Einstein condensate's practical limits will be found through experimentations, but honestly, their application could be stuff we can't even imagine.